Hi again. All right, so in the last video we talked about the normal distribution and how it's bell-shaped. We talked about its properties. What we're looking at here is going to be called the standard normal distribution, and we are doing that, it's based on the normal distribution, using what are called standard scores. Now you may or may not recall from a previous chapter, when we talked about percentiles and deciles and so forth, those measures of position, we also looked at what were called standard scores. And a standard score at that time was also called a z-score. Now in this case, we are going to be calling it a z-score more often than a standard score, but it would be the same thing. Now in terms of your z-score formula, you may recall this, you may not, but if you don't, it's on your formula sheet here under Chapter 6, Standard Score. So you've got that crutch if you need it, but you'll use it enough times in this chapter you won't need it. So z equals x, some value, minus the mean, divided by the standard deviation. Now at the time that we were talking about measures of position, we said that if a value of x was chosen, and that value is equal to the mean, if x equals the mean, then the z-score of that value x would equal 0. Which makes sense if you look at the formula. If I take the value of the mean and substitute it here, and I substitute it in place of mu, then in the numerator I'm going to get that value minus itself, which is 0. 0 divided by any number is 0. So anytime we choose a value of x that is equal to the mean, the z-score is 0. If we choose a value of x that is greater than the mean, then the z-score will be positive or greater than 0. And lastly, if we take a value of x that's less than the mean, then the z-score becomes a negative number or less than 0. And those are characteristics that we talked about in the previous chapter when we were talking about those measures of position. So let's assume for a minute that we have a normal distribution. Some variable that is normally or approximately normally distributed. We know that with that normal distribution, it has a mean at the center, and we know that numbers greater than the mean, because that x-axis is a number line, numbers greater than the mean would lie to the right of it, and numbers less than the mean would lie to the left of it. In a standard normal distribution, we're going to take all of these values out of this normal distribution, and we're going to standardize them. In other words, every number is going to be turned into a z-score using that formula. So if I were to take the mean and substitute it here in place of x, then I know this standard score, the standard score of the mean, is 0. That's what's going to create the standard normal distribution. So the standard normal distribution is a distribution where the original distribution was for a normally distributed variable, or approximately normally distributed variable, and we are taking every value in that distribution and changing it into a z-score. When that happens, the mean becomes 0, as we've said previously, and the standard deviation of that new set will be 1. Which means when we start looking at our empirical rule, if I go out 1 standard deviation to the right, and 1 standard deviation to the left, I'm now between -1 and +1 on that number line, and we know that this area should encompass 68% of the data values. If I go out 1 more standard deviation on each side, now I'm in this range of -2 to +2, then in this area, altogether, we should have 95% of our data values. And if we go out 1 more standard deviation on each side, then in this area, all the way across, we should have 99.7% of our data values. Which means, when we talked about outliers before, we said that one possible way to quickly identify excuse me, whether or not a number was an outlier or a possible outlier was to see if it lied within 3 standard deviations of the mean or not. If it laid outside that interval of numbers, or that range of numbers, then we suspected it as an outlier. and we could go through our process of checking for an outlier to determine if it actually was. That 3 standard deviations comes from this standard normal distribution and that empirical rule that tells us 99.7% of the variables should lie in that range. It also tells us that in this, the area of the graph between -3 standard deviations and +3 standard deviations, that the area in that portion is 0.997, which means the 0.003 that's left over is way out here in these little bitty tails. Not a lot of data there. So we're going to be using graphs of this type extensively throughout this chapter with that standard normal distribution. Now, the way that we're going to do that is to start finding the area under the curve. Making a distribution a standard normal distribution simplifies the process of finding the area under the curve because certain tables have been created that tell us the areas between the mean and a specific z value. Now, on your formula card, if we flip through, you'll find in this lovely little thing, table E, the standard normal distribution. All of these values on this sheet are the areas between 0 and z, and you see that here in the bottom corner. It's reminding you that the areas given in the table are between 0, the mean, and z, whatever the z-score is. And we can see along the top edge up here that these are our z-scores. So along the left-hand side of this table, we see the ones digit and the tenths digit, and we can see that it goes up to 3. We're not going to use much higher than that. We've already talked about why. And along the top, we see the hundredths digit of each z-score. So for example, here, if I were to use a z-score of 1.52, then I'd find 1.5, find 2, and that 0.4357 tells me the area under the curve between 0 and 1.52 for z. So in this case, there's my 1.52, here's my 0, and the area is that 0.4352. So each of these things are areas, and we know they're areas because the total area is 1, so these are all less than 1. The other thing that we'll notice, even as we go out to 3 standard deviations, and this one's at 3.09, if we look at the top of that column, that's saying that from 0 out to 3.09, way out here for z, that the area is 0.4990, which tells me that the other 0.001 is past 3.09 standard deviations. So each of these are areas based on a specified z-score, and the mean is set to be 0. So let's look at some examples then of how that's going to be used to compute areas based on that standard normal distribution. Now, I have a larger version of that table that I'm going to be referring to periodically, just so you realize that it's the same table. I'm just using it in a different form. All right, so with that in mind, let's look at our first example. We are going to be finding the area between 0 and z equals 1.37. And the process we want to use on each of these is always going to be the same. I want you to start with a sketch. I know some of us don't like having to draw things. Too bad. Get over it. You're going to draw them a lot. The sketch is going to help you visually see what you're doing. I know I say that a lot, but it's true. Okay, so here's my distribution. I know the mean here is 0, right at the center. And because this is a positive 1.37, I know it's going to be to the right of the mean. About there. I want the area between those two values, which is here. And we're going to shade that so we can kind of keep track of which part we're actually trying to find the area of. Now if you look at your table, remember at the bottom, it says that those areas given are between 0 and z. So in this case, it's just a simple matter of looking up 1.37 for a z value and seeing which area corresponds to it. So in this case, here's our table. We're going to go to 1.3. all the way across to 7, and we see that it's 0.4147. So this area is 0.4147. And that's the area between those two values. So this would be our answer. Now, if we do the same thing, let's find the area between 0 and, let's see, this time we're going to use negative 1.37. The same process applies. It doesn't change any. We're going to start with that sketch. You get to a point where you start to draw these faster. It's just a sketch after all. There's your 0 mark. Negative 1.37, because of the number line, lies to the left of 0. And we're still finding the area between these two values. But because the graph is symmetric about the mean, the area on the right side between 0 and 1.37 has to be the same as the area on the left side between 0 and negative 1.37. So the area in this case here is 0.4147. It is worth noting that we're talking about an area. Area is a positive number. You don't have a negative amount of area in your living room. It doesn't make sense. So areas are positive regardless of whether we're talking about the left side or the right side of the mean. Area is always positive. And that symmetric nature tells us that even though the values in the table are all positive values, we're still going to get the same area on the left side because of that symmetry in the graph itself. All right, so let's consider some other options then, because they aren't always between 0 and a number. For example, here we're going to look at, the next one we're going to find the area between let's see, we're going to use z equals -2 and z equals positive 2.14. So we're going to draw our sketch, label that mean. Here's our 0. All right, I've got one value that's negative. I'm going to draw that on the left. Not really concerned about how far away from 0 you draw that one, as long as you realize it's on the left. So if I were to look up -2 in the table, it would tell me this area. And in the table, when I look up -2, or just 2, it's 2.00, if we don't realize that, is 0.4772. 0.4772. Now let's consider this positive z of 2.14. If we look that value up, it tells us the value or the area between 0 and 2.14. Notice there's no overlap in those two. One's on the left, one's on the right. So we look up 2.14, and we end up with 0.4838. Now, if I wanted the total area of the two, then I'd follow what total means, add them together. So take 0.4772, and we're going to add it to 0.4838. And that total gives us the area that we're after, 0.9610. And that's that. Now that's only 3 of the possibilities. There are a multitude of possibilities for finding the area between values. In the next video, we're going to talk about some of the other scenarios and get through how to find the area under all these various circumstances. So, see you soon.